Welcome to this explainer. Today, we're tackling literally one of the most mind-bending paradigm shifts in all of modern physics. It's the realization that the information capacity of our three-dimensional universe, literally everything you see around you right now, is actually bounded by its two-dimensional surface area. We're going to explore exactly how black holes fundamentally broke our understanding of space and how the wild concept of a holographic universe was born to fix it.
Okay, here's our roadmap for this explainer. We're going to hit the information capacity paradox, black hole thermodynamics, the Bekenstein Bound, the holographic principle, and wrap it all up with Busso's covariant entropy bound. Let's get right into it.
Section 1. The information capacity paradox. We're starting with a fundamental assumption about the physical space around us, something so basic you've probably never even thought twice about it.
Seriously, take a second and ask yourself, how much data, or to be precise, how many independent quantum states, can you actually cram into the physical volume of the room you're sitting in right now? I mean, if you had some kind of ultimate sci-fi technology, could you just keep filling that space with microscopic hard drives forever?
Well, classical physics, and honestly our own common sense, assumes that, yeah, you can just keep packing information into a 3D volume endlessly. You just add more stuff, right? But the actual reality, governed by quantum gravity, is entirely different. The ultimate information capacity of your room isn't dictated by its 3D volume at all. No, it's strictly bounded by the 2D surface area of its walls. Crazy, right?
To really get our heads around this paradox, we need to define what information capacity actually means to a physicist. We measure this using degrees of freedom. Mathematically, sure, it's the logarithm of the dimension of a system's quantum Hilbert space. But let's simplify that. In plain English, it just represents the total number of fundamental bits of information you need to describe that system at a 100% microscopic level.
So traditional local field theory deals with this by chopping space up into an unimaginably tiny grid, right down to the Planck length. It assumes you've got at least one quantum oscillator, basically one bit of data, sitting inside every single 3D Planck volume. Following that logic, information capacity should grow proportionally with the volume of the space. In a perfectly continuous space, that implies the total degrees of freedom could literally be infinite. But as we're about to see, gravity steps in and completely shatters that assumption.
Moving on to Section 2, black hole thermodynamics. To figure out exactly why that 3D volume assumption is so completely wrong, we have to scale things way up to the most extreme gravitational objects out there, black holes. This is where we hit a massive turning point in physics. Researchers realized there is this absolutely perfect mapping between everyday classical thermodynamics and the mechanics governing black holes. Think about it. The constant temperature of a room mirrors a black hole's constant surface gravity. Energy conservation matches a black hole's mass-energy relation. And the really big one? The second law, which says entropy never decreases, perfectly mirrors Stephen Hawking's area theorem, which states that a black hole's event horizon area never decreases. This basically proved that a black hole's horizon area is literally a measure of its entropy, and therefore its information. Let's trace how this massive paradigm shift unfolded. Back in 1972, Jacob Bekenstein totally shocked the physics world. He conjectured that black hole entropy is proportional to its area, not its volume. Then in '74, Hawking proved that black holes emit thermal radiation, which locked down the exact math. Fast forward to 1993, and Gerard T. Hooft and Leonard Susskind realized this actually applies to everything, which gave birth to the holographic principle. Finally, in 1999, Raphael Busso swooped in to solve the remaining geometric puzzles with the covariant entropy bound.
All right, Section 3, the Bekenstein Bound. The crucial thing we're looking at here is how this extreme, weird quirk of black holes was mathematically translated into a universal rule for all ordinary matter.
Bekenstein realized something incredibly profound. Say you toss an object packed with high entropy right into a black hole. To an outside observer, that original entropy is just gone. But to stop the second law of thermodynamics from being violated every single time something falls in, the resulting increase in the black hole's area has to be greater than the information of the object that fell in. What does that mean? It means there has to be a strict, hard limit on how much information ordinary matter can hold in the first place, and we call that limit the Bekenstein bound.
Now, don't let the math here scare you off. The formula is actually quite elegant. The maximum allowable entropy or information of literally any physical system, whether we're talking about a cup of coffee, your laptop, or an entire star, is determined simply by its total mass energy and its circumferential radius. And that's just scaled by a few fundamental constants of nature, like the speed of light and the Planck constant. That's it.
We can actually prove this theoretically using what's called the Susskind process. Imagine an isolated system of matter. Now imagine collapsing a massive shell of material right onto it until it becomes super dense. Keep going, and you transform that system into a black hole with the surface area perfectly matching the boundary of the original system. Because the generalized second law says total entropy can never decrease during this process, the original matter's entropy could never ever have been greater than the final black hole's entropy. The takeaway? That original system was bound by the exact same area limit all along.
Section 4. The Holographic Principle. If we take this incredible discovery and push it to its absolute logical extreme, it fundamentally rewrites our entire understanding of reality.
Gerard 't Hooft and Leonard Susskind looked at these hard black hole limits and realized they were staring at something much, much deeper. They deduced that the area of any surface limits the information content of adjacent space-time regions. Basically, the fundamental degrees of freedom of our universe are tied to area, not volume.
Let's put a hard number on that, just to put it into perspective. This principle means our universe has a strict physical data cap. You absolutely cannot fit more than one bit of information into a single Planck area. In human terms, that is 1.4 times 10 to the 69th power bits of information per square meter of surface area. It's an unfathomably huge number, sure, but it is completely finite. And importantly, it only scales with the 2D surface, never the 3D space inside.
When you compare these two worldviews side by side, it turns out the 3D space we walk around in every day is effectively an illusion. We think we experience local degrees of freedom everywhere inside a volume, but the true underlying physics tells us our universe acts like a hologram. All the immense informational complexity of a 3D region is entirely and perfectly encoded right on its 2D boundary.
Which brings us to Section 5, Busso's covariant entropy bound. Because, as always in physics, there's a catch. When you start dealing with dynamically moving and shifting spaces, that simple boundary idea needs a serious upgrade.
Theoretical physicist Raphael Busso realized that the intuitive idea of just wrapping a 3D volume in a 2D spherical boundary totally breaks down under extreme conditions. If you try applying that simple area bound to, say, a rapidly collapsing star or an expanding universe, the geometry gets heavily warped by massive gravity. Suddenly, a fixed volume to area rule allows for violations of our strict information limit, and we can't have that.
To fix this glaring issue, Busso introduced a truly genius concept called light sheets. Instead of just drawing a static imaginary box around an object, you mapped the 3D regions to 2D surfaces using the actual path of light itself. You generate a light sheet by tracking imaginary light rays, moving perpendicularly away from a surface. But, and this is the absolute key here, you only follow those rays as long as they are contracting or converging together. So how exactly does this protect the laws of physics? Well, if you pick an arbitrary surface and fire these imaginary light rays away from it, gravity will naturally focus them. Eventually, because they're converging, they're going to pinch together and intersect at a point called a caustic. The moment they hit that caustic, you terminate the sheet. By doing this, gravity safely cuts off the enclosed volume way before it can ever hold more information than the area of the starting surface. It's brilliant. The geometry of light itself is what enforces the universe's data cap.
We've journeyed all the way from packing data into ordinary room-sized boxes to the absolute quantum limits of space-time and tracing converging light rays. The covariant entropy bound proves once and for all that the amount of information in our universe is finite, and it's strictly bounded by area. But all of this leaves us with one final, deeply provocative question. If everything we know, everything we experience in our 3D universe is fundamentally just a holographic projection of data, where exactly is the true 2D surface that's projecting our reality? We'll leave you to ponder that holographic illusion. Thanks for joining us on this explainer.